Thanks. Thanks for coming, and sorry for being late. And thank you, Scott, for wanting to give a talk. So I'll just give a brief introduction to you and how we met, and then I will hand the word to you to give a presentation of what you've been working on. So here in the Center for Computational Thinking and Design, we've had an interest in agent-based modeling since the beginning of the center, and I was looking for new tools for doing agent-based modeling and fell over Scott's tool that I tried to play a bit around with for a prototype. So I wrote Scott, and it turned out that Scott has a lot of interests that aligns very well with what we've been doing in the center. You have a background in also computational design that is super interesting from the perspective of some of the things that we were doing. And we've also recently just been granted some money to explore new tools for agent-based modeling, and more modern tools, where it would be super interesting to seek out potential for collaborating with you. So it's a great pleasure that you want to take the time to tell us a bit about your work. So I'll just hand it over to you, Scott, so I don't eat up your time, to take the word.
Okay, wonderful. Yes, and again, thank you for first reaching out to me. It's been really exciting to meet other people who are interested in agent-based modeling, and also the method of working on the web that this particular library has. So yeah, thank you, Clemens. Thank you, Marie-Louise, for coordinating. And I think I'll get started. I'm just going to begin sharing my screen, and just let me know if you all can see this here. This is the next slide of my presentation. Excellent. Great. So yeah, I'm going to be talking about Flocc, which is the name of my library for doing agent-based modeling. And we'll just get right into it. So just as an overview of this talk, I'm going to introduce agent-based modeling. I know that many of you are familiar with it, but for those who perhaps are not as much, we'll talk about what agent-based modeling actually is, how it differs from other kinds of modeling or simulation, and discuss why it's so adept at simulating complex systems in particular. Talk about some different contexts in which you might use it, so different areas that you can apply it to study. And I'm going to introduce Flocc, the library that's built using JavaScript, through 5 different models that come from a variety of domains, from physical and ecological systems to mathematical to political and social systems. So really, across all areas of natural and social sciences. And finally, we'll close by discussing some further applications of Flocc and how you might be able to apply it in your own research toward your own ends. So, but first I'm going to give a bit of background into myself and talk about how I came to encounter agent-based modeling and become so interested in it. So I originally studied to become an architect, and not a software architect, which is what I sort of identify as now, but a building architect. And I studied at Columbia University, but I learned pretty early on that architecture wasn't quite the right field for me, and that rather than thinking of architecture or buildings as just these individual objects or stylistic things to be designed, I was much more interested in architecture and buildings as systems. So that buildings are themselves these technical and material systems that are composed of different forms of concrete and glass that have these different material properties. They're also social systems, and the way that people use buildings has a great effect on how they function from day to day. I think this is something that actually many people are becoming more familiar with now, just as during this time of pandemic, people have been working from home, and their time spent around the house increases. Offices that have gone empty have also been affected during that time in terms of their energy consumption, in terms of just circulation and traffic patterns. And buildings are also part of these greater systems in the urban contexts that they're a part of. So after learning that, I was really less interested in architecture for the object itself as the systemic nature of it. I switched course and I entered another program, which, as Clemens mentioned, was called Computational Design. So this is another program where I really entered interested less in design or the outputs of design as the process of design. It was really exploring software for doing architecture and design. So one project that I worked on, you can see here, was sort of this free-form curve manipulator, where you have these points around the surface of a curve, very much like if any of you are familiar with Illustrator or other vector software, a Bezier curve where you can manipulate control points and endpoints, but for a three-dimensional surface as opposed to a two-dimensional curve. And this project was part of a software reconstruction. There was a group of students who were building these sort of almost archaeological reconstructions of software from the 60s and 70s in an attempt to uncover some of the both digital and material aspects of their interaction. And I was fortunate enough to exhibit this piece at SIGGRAPH, the annual computer graphics conference in 2018, and to have actual visitors be able to come up and use the physical control pad and knobs to be able to manipulate the surface, which was a great experience. But apart from the actual form, the visual form of design, what I became really interested in was how architects and designers specifically use simulation and modeling practices in their work. So one area that I spent some time studying was traffic, and in an urban context, how traffic patterns could be, one, modeled, and two, used as a context for designers to propose interventions into traffic and circulation systems around a city. So on the right is an early agent-based model prototype that I had built of these agents moving around an intersection, just sort of examine what emergent outcomes happen and how traffic jams could form and how they could be alleviated, and to explore that using agent-based modeling. So that's how I came to discover agent-based modeling and become interested in working with it as not only a designer and someone building, designer, researcher building models, but also working on the tools for agent-based modeling itself. So what is agent-based modeling? For those who aren't as familiar with it, it is a type of computational technique that, in my view, relies on two key steps. And the first one is the modeling, where within an environment, you model data as individual agents that follow rules of how to change over time. These are very abstract terms, and I think that's part of what makes it so applicable to a variety of domains, is that an environment is not necessarily a physical or spatial environment. It could be a conceptual or ideological space. In one of the political models, I'll talk about that. Individual agents are also not necessarily individual human beings. They could be, in ecological models, we'll see trees being the agents, we'll see birds. Agents can also be groups of individuals that you model as individuals if they function and if they move about as a singular unit. And the rules are just the computational piece that describes how change occurs over time. The second key step is observing the model. So I talk about both models and simulation, and I find the difference between modeling and simulation to be that simulation necessarily occurs over time and through these discrete time steps. And what you do is set it in motion and observe the emergent outcomes of the actions and interactions that take place both between agents and between an agent and its environment. So I had mentioned how in the example of a building, or in the traffic example, cars wear down a road over time. Cars and trucks wear down a road, and it requires repair and maintenance. So that's one way that agents can have an impact on their environment, which in turn, if a road requires construction, changes the behavior of those agents who are in the environment. So you have these notions of feedback loops that are coming into play as well. And so the broader question of why do we model, I think is best answered through a case study that we've actually already talked about a little bit. But I think that there are three main reasons why we might choose to model or simulate something. We model to explore the dynamics of complex phenomena. So to try to answer the question of why does this happen? Why do traffic jams emerge? Why does a physical system degrade over time, and how can it regenerate? We try to expose future system behavior. So given current conditions and the current assumptions that we built into the model, what happens if it runs for another minute or another hour or another year, and observe those changes over time to make guesses about the future behavior of the system. And finally, particularly as designers, people can experiment with interventions into systems. So how will it change if I add a lane to this road? What will that do to traffic patterns? Or what if I put a stoplight at this place? Or as a policymaker, if I increase or reduce taxes or penalties for certain types of behavior. These are going to be oversimplifications of the actual systems that they are a part of, but we can still gain information about how our beliefs and assumptions might play out into the future if we intervene in certain ways. So as I mentioned, I think talking over a real-world case study to kind of explore this a little bit further is going to be helpful. And I want to talk about how we might model the spread of coronavirus. Obviously, in the US, this is particularly urgent right now because cases have been increasing quite dramatically the last few weeks. After an early peak in April and then sort of a plateau where cases have still been coming in, we've seen them rising again. But the United States is a very large country. It's not homogeneous, and things are very different in one area to another. So in New York State, for example, where the epicenter of the outbreak originally occurred in March and April, in the US where it occurred in March and April, we had a peak of cases in April at around 10,000 cases a day that thankfully has been steadily declining since then. But on the opposite coast in California, cases have been increasing since the beginning and are continuing to do so, and don't appear to have peaked yet, if that is what's going to happen. We assume or hope that it will peak sometime soon, and we'll see a drop-off similar to New York State, but that remains to be seen. So I want to talk about, in contrast to agent-based modeling, how we might traditionally have attempted to model this kind of a system. And traditional modeling is often done through differential equations. So there's a specific model in epidemiology called an SIR model, which stands for susceptible, infectious, recovered. And each of those words or variables corresponds to a proportion of the population that is represented by that variable. So if I have not contracted coronavirus, I'm considered susceptible, and that I might be exposed to it and might catch it. If I do catch it, then I become an infectious member of the populace, and I am, potentially spreading that to other susceptible individuals. And eventually, as I recover, I join the group of people who are recovered. So each of these variables changes over time based on how large itself is. So the number of susceptible individuals depends on the number of people who are susceptible, as well as the number who are infectious. And as the number of infectious individuals increases, so does the susceptible individuals decrease because they're moving from susceptible to infectious. There's also this parameter here, the beta parameter, which plays a very important role in that it says how quickly people become infectious after they're susceptible. So the number of susceptible decreases at a rate proportional to beta times susceptible times infectious. And there's another one, gamma, which is essentially how quickly people recover from being infectious to moving into recovered. So there's these set of variables, and the choice of these parameters would let us have curves that are closer to New York or closer to California. This one here, we can kind of see this number of infectious individuals quite resembles what we saw in the case of New York State. Whereas in the case of California, if we wanted to be able to plot this, we'd probably need a lower beta parameter or we may need to adjust the number of individuals who start as susceptible or infectious. But we could probably approximate both of these cases using this model. That said, there are a number of limitations in this type of modeling that could be better explored through agent-based modeling. And some of these include the fact that all of our populations are considered totally homogeneous. So every susceptible individual is exactly like every other susceptible individual. But as I mentioned, we might want to model how different risk tolerance among individuals affects their behavior and the emergent outcomes. So it's not just that I'm susceptible, I become infectious at a beta parameter. It might be that I'm susceptible and I never leave the house. And so I have a much lower chance of becoming infected than someone who's going out to restaurants and bars and is engaging in riskier behavior. There's no spatial component to this model. So we might, if we're planners or policymakers, be curious to know how the geography and mobility of New York City versus Los Angeles affects the spread of the virus. In this type of model, agents also either have perfect visibility or no visibility. And what this means is in models where you have decision-making on the part of individuals, where agents have to take in some information about the environment, it's very difficult in traditional modeling to have a type of agent that only has limited awareness of the system around them, as opposed to either perfect global awareness and information about the state of the system, or no awareness. And finally, there's also a limited ability to represent and model hierarchies in traditional modeling. So we might be curious not just about individuals, but about groups and formations of individuals. So institutions such as local governments, state governments, the federal government, and how businesses and other organizations affect individual behavior, and vice versa. As individual behavior reaches critical points, how do they affect the behavior of institutions and governments? So I have here on this slide a visualization of essentially an SIR model, but implemented using agent-based modeling instead of the closed-form differential equations. We can see that it takes place on this two-dimensional grid, where we might consider that each cell on the grid is an individual in a city or some sort of landscape. But ones that have turned blue are infectious, and they may, with a probability that we could consider analogous to the beta parameter, they may spread coronavirus to one of the neighboring individuals. One thing that's interesting about this is we can see that there's two circles in the lower left and upper right quadrants that are darker colored. And this represents a higher degree of transmission from one individual to the next. So we might consider this people who are living in cities as opposed to less densely populated areas, or we might think about it as individuals who are engaging in riskier behavior. But either way, once the virus spreads from the center to these circles, we'll see that while it sort of fades out in the middle, it becomes much more densely located in these two regions. And if I were to let this model keep going on, it would remain there almost indefinitely, because this version of the model doesn't include a recovered population, only susceptible and infected. So we can consider this a disease where there is no immunity, where once you've caught it, you recover, you actually become susceptible again. And it's worth mentioning, this is not a model that I built myself. This is done by a researcher named Kevin Simler. It's called Going Critical, and I'll share the slides for this talk afterwards so you can see these links for yourselves. But again, to summarize some of the ways that this is, in my opinion, a version or a type of modeling that gives us a more nuanced and a more complex insight into system dynamics, is that we can have agents with diverse heterogeneous attributes and behaviors. We can represent spatial environments quite easily. We can have agents act with bounded rationality, only based on locally available information as opposed to the state of the entire system. And we can model hierarchies or groups of agents either as another type of agent or as the emergent outcomes of individual agents' actions. All right, so before we move on, I'm just going to pause and see if there are any questions about what we've covered so far. All right, if not, we can keep moving. And at this point, I'll start to introduce Flocc, which is the software tool that I've been building to do agent-based modeling. So Flocc is a JavaScript programming library for agent-based modeling. And I'm going to break apart some of these terms, again, for people who are perhaps not as familiar with them. But JavaScript refers to the language that Flocc is written in. So there are a variety of different programming languages, of which Python, C++, Java are some very prominent ones. JavaScript is the programming language that's used primarily on the web. And if you load any web that has a non-trivial amount of user interactivity and interactive functionality, it is likely using JavaScript in some capacity to provide that. So that makes it a really widely used language, and one that I would say has, again, this interesting affordance of being on the web, that if I write a program in JavaScript and I want to share that with someone, I don't necessarily, that person wouldn't need to download an application in order to run my software. They would just need to visit a website that's running it. And since basically every device, whether it's mobile or desktop, has a browser coming alongside it, that makes it accessible to a very wide audience. And the other piece of it, a programming library, is a bundle of code that abstracts certain functionality. And it allows programmers to ignore low-level implementation details. So this is sort of an important point, is that Flocc is not user-facing software. It's itself meant to be used by people who have some programming experience, ideally in JavaScript, although as someone who also writes some Python and other object-oriented languages, I think that there's a relatively shallow, but still a learning curve coming over from different languages. But a library allows programmers to ignore low-level implementation details. And what this means, I think I try to illustrate here. On the left, I have the 4 lines of JavaScript that would let me simply draw a circle onto the screen. So if I have a blank web page and I want to draw a circle on that screen, I would run this code on the left, which would then draw that circle. And it's not a lot of code, but if I'm drawing hundreds of circles onto the screen, if I'm creating some sort of visual pattern, I would want a way to be able to abstract and make it more reusable. One, so that I'm writing less code, but also so that it becomes easier to understand and to reason about what my code is doing, and to abstract it so I can extend it and reuse it in different ways. So I might write what's called a function, taking these 4 lines of code and turning it into 1 line of code, which I could just call, and it runs all of the code inside this function. So if I encapsulate this into a circle function, I could just draw this line of code, and it would draw the circle to the screen, giving it these different parameters, which allow me to draw it at different positions or at different sizes or with different colors. So this is a somewhat trivial example, but this is essentially what Flocc does for agent-based modeling. Rather than having to write the underlying code to represent agents and to have them update, and for things also like graphics and visualization, Flocc provides these functions, or this encapsulated functionality, to allow programmers to write code at a different level. So again, just the important caveat that Flocc and programming libraries in general are not graphical user interfaces. They're not able to just be opened and pointed and clicked and interact with by a non-technical user, but they can and usually are used to build other applications, including but not limited to user interface software. And with libraries, programmers can take advantage of this reusable code to write programs at the level they desire. Again, the intended audience being someone who is interested in agent-based modeling or in simulations, but doesn't want or isn't able to write the low-level graphics visualization code may not be familiar with as many statistical algorithms, and all of these are things that Flocc provides to be able to build models with. And in summary, with Flocc, programmers can design, run, visualize, and analyze agent-based models, writing far less code than they would otherwise. So I think with this context, this background into agent-based modeling, and now a brief introduction to Flocc, it's time that we can actually look at some models and do some hands-on modeling using Flocc. So I'm going to begin with a very simple example, and this is not the most realistic model, but one that will just help us to understand how Flocc works. The motivation for this one we might consider as a sketch of the behavior of people who are forming a queue. So these agents or individuals represented as black circles on a horizontal line across the screen, they just try to get to the horizontal center of the screen. And once they're there, they don't want to get too close to other people, which we might consider protecting one's own personal space. And so they sort of bump and jostle each other out of position as they attempt to stay at the center of the screen. So I'm going to switch to a new tab now where I have this running. This website or this application is called Code Sandbox, which just lets me run code in this one panel here and see the output visualization of it immediately. So if I make any changes here, we'll see it update on the right immediately. For example, I set my initial width and height of the environment on line 3. If I change the height from 500 to 300, then we should see this refresh on the right and update with a more horizontal rectangle. So there are 3 elements of every Flocc model that give it the core functionality. And those are a tick function, and a setup function, and a run function. And actually, before I dive too much deeper into this, can everyone see or read the code on my screen relatively well? I'm
yes.
seeing if okay. So if you're familiar with NetLogo or some other software for agent-based modeling, these setup and run functions will probably be familiar. These are, like the setup and go buttons in NetLogo. And they do what they say in English. The setup function is where I set the initial conditions and parameters of the model. And the run function, which is quite short, just sets it into motion and keeps it running indefinitely unless I implement some outside factor to stop it. There's not a pause or a stop button. I typically just use some of the built-in features of the browser to do that. If I want to start it over, I can click the refresh button on my window and just take advantage of that to rerun the model. And I'm going to dive into the code for this model so we can see and gain some insight into how it's functioning. This is the only one that I'll go really into the low-level details of how the code works. In the subsequent models, we'll just look at the emergent system behavior and talk about how you can influence it using the library. So if I expand this, within my setup function, on line 43, I have this for loop, which is just a statement that allows me to execute a piece of code a number of times sequentially. So I'm saying 10 times I want to run this code inside this block. And what I do here is I create a new agent, I add the rule to it, the tick update rule, and then I add it to the environment by calling environment.addAgent. So an agent itself is simply a set of key value pairs of data. So I have keys, which are the names of the pieces of data, like a color, an X value, a Y value, and a size. And I assign values to each of these as I instantiate the agent. So I say its color is black, but I could just as simply have said blue. And when it refreshes, we'll see that we have blue agents on the screen as well. So the color and size in this model are really just about the output of the visualization. What is important for the behavior of the model are these X and Y values. And I set them up so that everyone starts with the same Y value, which is what puts them in this horizontal line across the screen. And everyone has a different x value related to this I variable, which I get in the for loop, but which lets them have different starting x values. And so on line 50, I add this tick rule, and this is what tells the agents how to update with each discrete time step of the simulation. If I expand this, we can look at it, and this may look a bit obtuse at first, but we'll walk through it together, and I'll describe what's happening. So initially, I get a reference to the agent's x and y values. I call agent get data, and this returns all of the data associated with it, including the color and the size. But like I said, only the x and y values are relevant for this model. On lines 15 through 19, I compare the agent's x value with width over 2, which is the horizontal center of the window. So if their x value is less than that, then I write x++, which basically means to increase the x value by 1. Otherwise, if it's greater than that center, I decrease it by 1. And so that means that any agents who are on the left-hand side will move to the right, and vice versa, on the right, move toward the left until they approach the center. Just to see that running again. So on line 20, I also have this line that it may not be immediately clear its purpose, but has a really important effect on the model. And this line of code just tells the agent to update its y value by either 1 or -1. So this introduces some noise into the model, or some randomness. It's what causes these agents to be sort of moving slowly, randomly in the vertical direction as opposed to horizontal. If I were to comment this out, we'll see very different behavior emerge, and it becomes much more almost robotic and machine-like. So rather than sort of slowly moving up or down, all of these agents are moving perfectly horizontally across the screen. I'll refresh that one more time, and as they reach the center and as they collide with another agent, they can't go left or right any further, so they're only going down across the screen. So, this might be a model of some other type of behavior, a conveyor belt, or something where you have this perfect vertical motion, but it becomes much less useful and much less realistic if we're talking about human behavior. So I think that randomness and noise is a really key ingredient into building realistic models. And lastly, on lines 21 through 35, I'm running some code that does what in computer graphics is called collision or boundary detection. But basically, every agent is considering every other agent in the model. And if it's too close to any other agent, which is on line 20 here, this distance function, if the distance between the current agent and one of its neighbors is less than 10 units, then we're going to move away from it. So if their x values are too close, we're going to either decrease or increase the x value, and same for y. So if I were to turn this off, I'll do that right now. If I were to comment this out, we'll see everyone move toward the center, but then overlap with each other. And these aren't actual physical objects, they're digital representations. They don't take up any real space. So if we want realistic or naturalistic physical phenomena to happen, we have to take into account the fact that they should have this space around them. And given that we're talking about modeling humans who are not able to overlap in the same physical space, that's something that we have to implement. But Flocc provides this distance function, the ability to loop over other agents, and to avoid collisions. And lastly, what I do after having updated these x and y values is to return them out of the function. And this tells Flocc, or the environment that's running the code, to now update these on the agent. So if I had kept all of this, updated the x value, the y value, and done the collision detection, but not returned this out of the function, we would see just a static model. So no change happening, because although it's doing the calculations for updating, it's not actually setting those new values. So by returning those, we can have the agents update at each step over time. So this is, in a nutshell, the high level and some of the implementation of a model using Flocc. And I'm just curious if there are any questions on any of this or anything that I can go into any more detail on.
So just the core feature here you're using is the time tick and the sampling.
Correct. Yeah. So this sample. Yeah, I didn't talk about this function specifically so much, but this sample is a utility function that Flocc provides that lets me retrieve a random item from a list. So I have the options here being 1 or -1, but I could have it be 1 or, let's say, -5. And we'll see now that more often they're moving in this kind of silly manner up the screen, because half of the time they're moving down the screen by 1, and the other half of the time they're moving up by 5. And you can include, as many items into this list as you like. One other way of implementing this type of random noise would be to use some sort of distribution. So I'm using discrete integer values here of either 1 or -1, but I could also write utils random -1 1 true, and this looks relatively similar, but now we're using decimal point, floating point values. So an agent might increase its y value by 0.25, or it might decrease it by 0.8, but we're working with values in between -1 and 1, and a distribution uniform across that range rather than discrete 1 or -1. And these are, again, choices that a modeler can make that will have a pretty big outcome on the effect of the model. Where and how and to what degree randomness is used to achieve certain behavior can have a big outcome. All right, so I will keep moving on now and get into some larger models and some more interesting models. So the first one that I want to present is a flocking model. And I will say also that most of these models that I'm presenting, I did not originally conceive of and come up with. So this flocking has been around for over 30 years and was originally developed by a computer graphics engineer. It was used in computer animated films in the late 80s and early 90s, but it was really an attempt to sort of naturalistically simulate the flocking behavior of birds or schools of fish. What I think is really sort of beautiful about this model is how it so succinctly illustrates how complex emergent behavior can arise out of the interaction of very simple rules. So there are 3 rules that agents follow in this model. And we see these groups or flocks of agents begin to emerge and to disperse and to move together across the screen over time. And I have this running again in a code sandbox. I was doing some work on this and introduced a bug into the code, so intermittently it may crash on the right, but I'll just keep refreshing it until it works, which it appears to be now. So again, I'm not going to dive through all of the code for this model this time, but I will talk about some of the important parameters that influence the behavior of agents and the outcome of the model. So there are 3 high-level parameters called alignment, separation, and cohesion. And if you're familiar with NetLogo, and you might have actually even seen this model built using NetLogo, you're familiar with the sliders that you can use to adjust these. But we can, just going in here to the code, type in values between 0 and 1 in order to adjust the degree to which these variables are present in the model. So alignment refers to how much an agent will turn toward, will turn so that it's moving in the same direction as its neighbors. So these agents are all followers. There's no leaders who are moving in an opposite direction of the group. Everyone wants to turn toward the same direction as the group. If I turn this from 1 down to, say, 25%, we'll see that there's not really yet much group formation happening. And in this version, agents are much more reluctant or slower to turn their heading to match that of their neighbors. If we let it run for much longer, I think we would eventually see groups start to form. It seems like there may be some happening, but they don't retain their formation as a group nearly as much as if we turn it back up to 100%. Separation refers to what I had mentioned in the first model, that trying to keep some sort of physical distance between oneself and one's neighbor. So although they're turning in the same direction as their neighbors, they also want to keep a minimum distance between themselves and any other agents. And if I turn this off, we will still see groups form, but it's going to appear as if agents are just disappearing, because we see them immediately start to overlap each other and occupy the same physical position and move in the same direction. So it almost looks like, again, agents are disappearing from the model, but in actuality, they're just overlapping. So we might have 10 or 20 or 30 agents on top of each other at one position. And the last variable that really affects how the flocking occurs is cohesion. So an agent will want to move toward the center of, sort of the center of gravity of the agents around it. If I have one agent to my left and 3 to my right, I'm going to move to my right to be closer to the center of those 3 as opposed to the 1 on my left, while still respecting that separation rule and not getting too close to another agent. And if I turn this off, then we'll see there's really not much flock formation, but we do get agents moving in the same direction. So we get almost these more diffuse groups of agents moving continuously in the same direction across the screen. And actually now most of them are moving either up or down, although they're starting to move. So this is, you know, maybe closer to a simulate, like a fluid simulation, and how you might simulate water particles or some other natural as opposed to social system. The last parameter here that I'm going to adjust is the vision, or how wide of a radius an agent considers outside of itself to make decisions with. And this is that bounded rationality that I had talked about. So it's set to 15 right now, but if I increase this to, say, 60, we're still going to see flocking behavior, but it's going to occur very differently. Agents are sort of sucked in from a larger distance away into these flocks, which then become much more diffuse over time. I'm not sure how well you can tell based on the connection, but it's also moving somewhat slower. And that's because it takes longer to do the calculations and the computation for a wider radius of agents than it does a smaller one. So if I turn this back down to 15, we'll see that bug that keeps appearing, but we'll see that original flocking behavior. Right, and I'm going to close this one to keep us moving along. The next model that I want to show is called a forest fire model. And this is, you know, what it says on the face. It's a model of how a fire might spread through a forest. But the motivation is also to demonstrate how, beyond a certain point, model behavior can drastically change in an unpredictable and nonlinear manner. And we're going to see how a small change in the density of the forest can greatly impact how far the fire spreads across it. So at the start of this simulation, I generate a forest, which is randomly composed of either trees or empty space. And at the beginning, it's 59% full of trees. which turns out to be, as we'll see, an important threshold. If I set this to, say, just 2% full, we'll see a screen that's almost entirely black with a few dots of trees. And notably, we also don't see any fire spreading across it. And that's because the update rule in this model is that any agent or tree who is neighboring a tree that's on fire will catch on fire. And each agent considers its neighbors to the north, south, east, and west, and says, are any of those on fire? If so, I am catching on fire. If I reset it to 59%, again, we'll see this fire that starts at the left and right edges of the window spread out through the forest. And 59% is a really interesting threshold because most of the time we will see a great majority of the forest catch on fire. At the end, once it stabilizes, there may be some remaining areas or regions that have not caught fire, but we're typically going to see most, if not all, of the forest catch on fire. However, below 59%, this is rarely the case. And if I bump it down to 58 or 57%, we're going to see what looks to be probably a very similar forest. To our eye, doesn't appear that different in terms of density, but our fire is going to stop and leave this large region of the forest untouched. I can refresh this a few times, and the outcome, although it is randomized, the outcome is almost always the same, that the fire is not going to spread throughout the entire forest, or the left and right are almost never going to meet each other in the middle. Above 59%, however, I turn this to 60%. Again, from our eyes, the density is going to look very similar, but at this parameter, this level of density of the forest, the fire nearly always is going to spread across the entire forest, leaving just a few small regions untouched. I'm going to run this one more time. That was actually larger than I expected, but I think in most runs of the simulation, we'll see very small regions that are not exposed to the fire, and we're going to see it continue and almost always meet from left to right and take over the entire screen. So this 58 or 59% is what's called a critical point, or a tipping point, where making a small adjustment to this parameter can have a greatly outsized impact on the overall model. And although I've been calling this the forest fire model and talking about trees catching fire, this is actually also a variation of the SIR model, where we only have susceptible and infectious individuals, susceptible being trees that haven't caught on fire, and infectious being those that are on fire. We might consider this also people who have a virus or people who don't have a virus. And this model doesn't include that recovered aspect, but there are variations of the forest fire model that do include that to explore how those dynamics affect it. Both the SIR model and the forest fire model are themselves variations of a transmission model. So any type of model where you're exploring how something is transmitted across a network, whether that is fire or viruses, or if it's ideas, these are all things that have been studied using transmission models. This next model is really not an agent-based model, but I think is a really interesting and compelling, from an abstract mathematical perspective, model for discussion, and also illustrates something unique to Flocc as a JavaScript library, I think. So this is called a Lorentz attractor, which is named for Edward Lorenz, who was a meteorologist. He was also the person who coined the terms chaos theory and the butterfly effect, if you're familiar with those, which is just the idea that within any system, there are, as we saw in the last example, there are ways in which making a small change can have a dramatic and a drastic impact on the overall behavior. So the Lorentz attractor is actually just a set of 3 differential equations, like those differential equation-based models I discussed at the beginning. And the 3 variables are x, y, and z values. So it takes place in 3-dimensional physical space. And it starts with these 5 points, which if I refresh, we'll see they start very close to the center, and they follow initially similar trajectories, but over time we see them start to diverge from each other, and at a certain point there appears to be almost no correlation between one point and the next, despite their having started from such similar initial positions. That said, although all of them are on different trajectories right now, and none of them are following the same trajectory, they're all collectively tracing out this path that swirls around these two vortices almost. If I move around on the screen and rotate, you can see how it forms this three-dimensional shape in physical space. And this is what's called the attractor, that all of them are following unique paths, but globally they're following a pretty well-defined, or tracing a well-defined surface. And from the perspective of a library writer or a programmer, what's nice about this is also that I'm using Flocc alongside another library to do the 3D rendering. So in all of the examples we've shown so far, Flocc provides all of the visualization capabilities. However, there isn't any built-in 3D visualization, so I'm using Three.js, which is a JavaScript library for doing 3D visualization alongside Flocc, to be able to show this really, the emergent behavior of the system, which wouldn't be captured nearly as much in 2 dimensions alone. And you can use Flocc alongside just about any open source JavaScript library, whether it's for 3D visualization or you want to introduce an audio component to the model, or if it's another form of 2D visualization that Flocc itself doesn't provide, you can use it alongside libraries to write code that takes advantage of other pieces of functionality. The last model that I'm going to discuss is called the Iowa caucuses model. And this one is actually an original model. So I wrote the code for this, but also conceptualized it and was really interested in simulating this particularly unique political event that takes place in the United States every 4 years. So at the start of the presidential primary cycle, this is an event that takes place for both of the major parties, the left-wing Democratic Party and the right-wing Republican Party. But it's not a traditional electoral event or a blind event where you cast a vote and the winner of the most votes is the winner of the event. In a caucus, there are a number of candidates. In this one, there's 8 candidates. And as a voter, I might go to the caucus, cast my vote for a candidate, and if my candidate does not receive at least 15% of the vote, then I, as the voter, have the opportunity to cast my vote for another candidate. And so this continues until all candidates who are remaining have received at least 15% of the total vote. What's also unique about this is it's certainly not a blind event. In fact, it's actually quite social and quite argumentative and debate-based. And I will have other voters from candidates A, B, and C coming over to me trying to convince me personally to persuade me to change my vote to their candidate. So it's really interesting in modeling how both political ideology and this social network affect the dynamics of the Iowa caucuses. So, and this model uses a few other features of Flocc that I haven't discussed yet. The first is a histogram renderer. So this shows distributions across the set of agents. So in this case, it's depicting how many votes each candidate received. So red, orange, yellow. Red is seems like the runaway winner at this point. At the start, each voter who are represented by these small circles cast their vote for the candidate, or these large circles, who is closest to them ideologically. And I'm mapping this out on a political compass. So we could consider moving from left to right being the economic positions of a candidate, and from top to bottom being their policy style from authoritarian or centralized government to libertarian or individualist free market. So we have this green candidate who's the perfect centrist, but who in this case actually did not receive that much of the vote. Given that when I created this model, earlier this year, it was the Democratic primaries that were in full swing, I did situate most of my voters across the left end of the spectrum. So it appears like it's black who is closest to the center from left to right here and from top to bottom, who's received a great number of votes. But we also see that, red has a large number, purple as well. And what happens on subsequent rounds is if, as I mentioned, my candidate doesn't meet that 15% threshold, then I look to my friends or coworkers or neighbors for advice. And if I have 4 friends, or we can call them connections, which are drawn with these lines between voters. If I have 4 connections, 1 of whom has voted for candidate A and 3 of whom voted for candidate B, then I will have a 25% chance of changing my vote to candidate A and a 75% chance of changing it to vote B. So I sort of take in the information that I have coming from my connections and make a decision that's weighted based on that. But it's not a simple, the majority of my friends say I should vote for B, so I vote for B. I do take into account that one coworker who has voted for candidate A. And another element that introduces some noise or some variation into the model is the fact that there are friendships that stretch across ideological lines, or maybe these are familial relations. There's one I'm looking at here where a pretty far left-wing voter has a connection to someone who's much closer to the center. And by virtue of that, if this voter's candidate didn't meet the threshold in the first round, they're going to be taking in information from some voters who are quite different from them ideologically. And the spread, or again, the transmission of votes for candidates across this network is going to be informed by those dynamics. And so I mentioned, one other piece of, or class within Flocc that this model uses is called a network, which has let me draw concrete connections between agents, or to model connections between agents, which is something that we haven't shown in any of these models yet. And I'll just run it one more time just so we can observe. At the start, everyone has 1 vote. All of the candidates are voting for themselves, but we can see the different colors transmit across the network over time until eventually, at this point, yellow is out, orange's votes are dwindling. It seems like red and cyan are poised to take the most votes in this run. There's a small cluster of blue voters, but those are gradually being persuaded to vote for another candidate until at a certain point, all of the remaining candidates have at least 15% of the vote. All right, so that was the last model that I wanted to show, but if there are any questions before we go on, I'd be happy to go back or discuss any of the models if there are things people are curious about. No one wants to be the first one to say anything? All right, we can keep going and I'll leave plenty of time at the end for questions as well. So finally, I just wanted to talk about some further applications of Flocc and how you hopefully might be able to use it in your own research. So one of the top level areas that I'm very interested in, I think could be really useful for, is in building more interactive models or simulations. These are often called explorables, but there's sort of this movement or this style of, I would say almost journalism on the web, where people build these longer interactive models. So I mentioned Going Critical earlier, and this is that SIR model built by Kevin Simler. But this is really a long article where he describes diffusion across a network, talks about how the grid that was in that model is really a generalization of a network where every agent has exactly 4 connections. You can represent it as a grid. And it's also interactive, so I can scroll through this and click play and pause. Again, really similar to a NetLogo model where you have this interface for it, but built into the web, and taking advantage of the web as a medium for that. You would also be able to use Flocc, as I mentioned, as you use any programming library to build other applications, and specifically to build graphical user interfaces for agent-based modeling. So I actually have a prototype of one that I'd like to show. This is something I've been working on recently, which is a user interface for manipulating cellular automata. So cellular automata, we just saw it with Going Critical, and we saw it in the forest fire model also, but it's a type of model that takes place over a grid. And this that I'm showing right here is a specific type of automata called the game of life, which only has two values. The cell is either dead or alive, or in this case, black or white. And the rules are depicted here on the left-hand side. So these rules state, in plain language, all cells will turn white if there are exactly 3 white neighbors. But I could change this from 3 white neighbors to 3 black neighbors. Now we'll see that the dynamics of it are quite different. If I change it from exactly to, let's say, at most 3 neighbors, no, let's do at least. Okay, well that will just give you a seizure if you look at it for too long. So building this is one way to sort of extend, again, the audience who can work with this. And now this type of modeling is not just limited to people who have programming ability, but anyone who can interact with an interface like this. And finally, one area that I have an interest in, and I imagine many of you do as well, are in simulation-based workshops or activities. So where you're either using modeling or simulation to explore how people would make decisions about something, or about how they leverage computational thinking to achieve some goal or consider something. I had mentioned some of the research that I did into traffic modeling. And part of this was also an in-person workshop with a number of designers who I wanted to consider different factors that that come into play with traffic in an urban setting. So I had this sort of silly icebreaker activity where I set up a simulation, or a physical simulation of an intersection, and had the designers walk around this intersection just to consider what are some of the things that they think about as drivers, and what are some of the physical factors that affect the system of traffic. And I followed this up with a digital activity where we attempted to model some of those factors, and included things like stoplights and regional variations in driving patterns. This was actually in Pittsburgh, where Carnegie Mellon is located. There's a sort of interesting regional behavior where drivers will often turn left at the start of a green light, which is not really common throughout the rest of the United States, but that was one thing they were considering as a factor and trying to model. And so, at this point, Flocc hadn't yet come into being, but if I were designing a workshop now, I would certainly make use of Flocc to try and build some sort of interface, or to allow them to manipulate and play with models in a way that is more tangible and hands-on, and gives them the ability to experiment with interventions into systems. And so I think all of these are really fruitful avenues for research, all ones that I hope might spark some ideas or interest on your end, but I think are the future of Flocc, in addition to building it out as a library and continue to make it more useful to researchers, scientists, designers, and to people who are interested in simulation. So thank you all again for joining. At this point, I'd be happy to take any questions about Flocc or any of the models, or anything else you're interested in knowing.
Thanks, Scott. So if any of you have a question, please speak up or raise your hand, or what you prefer. I can start asking one question, Scott. So have you made any thoughts to how Flocc could be used as a tool to teach modeling? As you said yourself, some of the examples when programming JavaScript is a bit obtruse. Are there ways to make it more accessible to beginners in modeling?
Yeah, one thing that I haven't shown yet is the website for Flocc, which if you are interested, you can visit at flocc.network or www.flocc.network. So I think that, like I'd mentioned, that these explorable style simulations, this is really almost like a tutorial also, but one that has these built-in, I enter it and I'm able to not just read a description of something, but press a button and sort of see it take place over time. I think it's a really powerful way of learning about these sorts of dynamics, this SIR model, but also could be used to expose how you might interact with the tool. Brett Victor, I'm not sure if you're familiar with his work, but he's done a lot around this. He has this article called, I think it's Climbing the Ladder of Abstraction. That's really, I'm not going to be able to find it. I'll see if I can find this. Here we go, Up and Down the Ladder of Abstraction. But this is early in internet terms from 2011, sort of explorable style article where you can scroll down and be able to simulate this. But this is really about computational thinking and about this car doing what happens in an agent-based model, which is at each discrete time step, it moves forward by 1 pixel. If it's left of the road, turn right by 2 degrees. So it's following these simple rules and letting you see how they play out over time. But I think absolutely building interfaces that let people interact with them directly is the way to help teach more effectively.
So I guess that's one side of teaching modeling, is to build these explorables that enable you to, or help you think in these ways. But the other side of of it would then be how do you help people build or use Flocc to experiment with modeling through programming?
Yeah, I can show just a little bit more of the website, but I've attempted to, I haven't gotten a lot of feedback, but I've tried to make the documentation on this site useful. So this is pretty dry and programmer-focused documentation, but if I want to learn about the interface for the network helper, the network class in Flocc, I can visit this page, which talks about the different methods that it has. So, a network, you can add an agent to it so that it's now a part of the network. You can remove an agent. You can connect two agents. So I think, just from the standpoint of a programmer or someone who's already familiar with JavaScript and with using third-party libraries, the documentation, and I think also combing through these examples as case studies for how to build models are the things that hopefully would be good teaching tools.
Right.
Okay. Thank you for your talk. That was very interesting. One thing that I was wondering about, and use that I could see for tools such as your library here, is for software testing. I often have students who build complex distributed system with many potential users, and being able to model different kinds of users with different kind of behaviors and having them interact with the system through whatever API the students have built could be quite interesting. Has anyone used your tool for software testing or something along those lines?
No, I would say not yet. And there are a few limitations for it right now, which are part of my ongoing summer project in making it more usable. But one of those is, so I talked about the importance of randomness. But the flip side of that is that you would prefer to have predictable or at least repeatable randomness. And currently, Flocc doesn't include any seeding for randomness. So whenever, if I open the Iowa caucuses model again, every time it's instantiated, it will be completely different. But if and when seeded randomness becomes implemented, you could say, okay, seed this model with a value of 1 or 10 or 100, and then every time you rerun the model with that seed, you'll have the same pseudo-random results. But that notion of replicability is something that I think would be really important in extending this, and in being able to use it, specifically for testing and verifying results. The other thing, I've shown some of these renderers, and there's a histogram. There's also a line chart renderer for showing changes in values over time. But one thing that I think would be important, or hopefully would be useful, would be just a simple table renderer. So if you have, a series of agents with different X values, or these voters with, candidates with different number of votes for them, just to be able to visualize a table and be able to click for from ascending order of a certain value or descending, or to be able to filter results. Having some way to quickly view an interface for that, I think would also be really important. And I think hopefully some of those speak to your questions.
Yes, certainly. Thank you.
Questions? Line?
Hi, thank you very much for this talk. It was really interesting, and I really like how you can update both the sort of the interface and continuously, as opposed to when you use NetLogo, which that I've been using. But I'm wondering about the educational settings. Do you know of any situations in which this has been used for traditional school settings, or throughout K-12 or some similar settings?
Yeah, not yet would be my answer again. It's still a very young library, so it hasn't seen very much testing outside of, I know a few of students and staff at my university, Carnegie Mellon, have used it. And there are a few software developers who've used it on their own. Candidly, I think that part of its being a programming library is, in some ways a hurdle toward using it in pedagogy, only because not everyone can look at what's happening on the left and know how to manipulate this in a way that if I just, delete a letter here, the entire thing will go up in flames. Yeah, it throws an error. So, the nature as a code library does make it more fragile. But like I said, and I believe it also makes it powerful because you can use it to build other interfaces. So my hope is really that things like the cellular automata builder, I'd love to also work on an interface for developing rules in a discrete spatial environment, like a flocking model. These are ways that I think would provide a lower entry point to doing modeling, but in a way that gives you, the benefits of working with the JavaScript environment on the web, and where someone doesn't necessarily have to learn a programming language in order to be able to use it.
Yeah, because I think what we've been trying to do is to actually implement both modeling and coding in the same activity in regards to whatever text that they've been teaching in the subject. And I think what we would like to do is for students to look at both the programming and also the interface, the simulation as well. And what I like about NetLogo is that it sort of has a, as you said as well, a low threshold. So you can get everyone looking at some pieces of code or a piece of a program. actually identify with the agents, which is would maybe be my concern with this, that would they be able to sort of identify the agents, and would they be able to sort of feel their way through the program and see what's actually the properties and behavior of those agents. Yeah. But that'd be interesting to see.
I think also, Scott, you emphasized that it is really a library. So I suppose that it would be possible with Flocc to explore different ways to make the connection between, controlling the model through user interfaces and exposing the code. And I guess that's one of the strengths from having you build it as a web library, that you can potentially hide away some complexity and expose only a little of relevant code, for instance.
Mm-hmm. Right, exactly. I think hearing you say that, I think also that there's probably sort of an intermediary step where it's maybe not as user-friendly as this interface, where I'm just clicking to add or remove or change aspects of it, but where I could write a function again that encapsulates the code to build a new agent and call that like a simple agent function, where I only pass certain parameters to it, and the rest of those would be baked into it. But that would be a way, I think, of addressing, Lena, some of your concerns to make the programming less. There are many levels to it. There's a very low level that's being abstracted away. I'd say Flocc itself is at sort of a mid-level where you're including all of the relevant key value pairs of information, but then there's maybe a higher level that's not quite at the level of a user interface, but where I'm still writing code and passing in variables and parameters to it, but in a more simplified way than I have in some of the example models.
Yeah, thank you.
Ole?
Perhaps, well, first of all, Scott, thank you so much for a very interesting talk. Perhaps my question is sort of along the line of what Lena was saying, because we come from this sort of educational sort of interest in computational thinking and modeling. Mm-hmm. So have you given any thoughts or considerations about sort of Flocc as a collaborative environment for, let's say, programmers, or in our case, students that want to collaborate on both understanding and doing the modeling, as well as understanding and doing the coding?
Yeah, well, it's funny that you mentioned that. That was actually one of the things that I think Clemens had reached out to me about originally, and part of his prototype, I'm not sure, Clemens, if you've shared it, but was using code straits alongside Flocc to have a modeling environment where, if I were to be able to share this link, we could look at the same model at the same time, but both be able to adjust it or manipulate things about the model. So I think that's a really, potentially fruitful area of collaboration and future research. I do think it's something that's outside sort of the scope of Flocc itself as a general purpose programming library for agent-based modeling, but is definitely an application that I think is worth exploring.
Yeah, I get what you're saying. It's just that our interest is so much sort of concerned with the educational aspects. Mm-hmm. So we do see that that the modeling in itself is very interesting on this particular sort of application area. The thing is that we need also to consider how this would work, like in teams of students working on modeling, right? And I think that is essential, the way that that they will sort of address or approach modeling when it comes to education, like in groups of students working on the same model. Mm-hmm. Well, thank you. Absolutely.
Other questions? All right. Then thanks, Scott. It was very interesting, and I think it also was a nice way that you introduced what agent-based modeling is with nice examples. I think it was a very nice presentation, and I'm excited also to see what the uptake of Flocc will be, since it's a very new library that you've made, and I'm also looking forward to experiment further with it. within some of the projects that that we will do, and we'll definitely reach out to you for help and ideas when we get to do that.
Yes, I look forward to it.
Yep.
Thank you again for having me.
Yep. Yep. All right. And with that, thank you all for coming and asking questions. So, have a nice day, Scott.
You as well. Thank you.